So let's look at crown ethers, and we saw that metal atoms with a full or partial positive charge can be stabilized by ether solvents. And already we know the reason. We know the reason why. Because the ether is negatively polarized. It carries a negative dipole. As a result, it can interact with the magnesium metal and thereby stabilizing it. And another reason why ethers are good solvents for carrying out Grignard reactions is that they do not have an ionizable proton, which can destroy the Grignard. And so that is a huge advantage, because you recall, in the presence of an ionizable proton, the alkane is formed with the formation of the salt. Now, crown ethers have been shown to form especially strong attractions for metal atoms, and that's because they're able to solvate the metal cation. As you can see here, if you have a metal cation trapped in the middle, it can be solvated by the dipoles on the oxygen, the negative dipoles on the oxygen. And so typically you can have lithium sitting in here. You can have lithium metal that's much smaller, and in this larger one you can have sodium cation, and here you can have potassium. See? And so that interaction can occur here, the negative charge, negative charge, negative charge, and so it ends up trapping. So the size of the ether will determine what metal cation it can trap. Now, note how many carbon atoms are separated the oxygens. These are called crown ethers. As you can see, it's as if the ether is sitting on top of the head of the metal cation, so it looks like a crown. Okay. Now the numbers 12 simply signifies the total number of atoms, while 4 signifies the number of oxygen atoms. So 15 in this case signifies the total number of atoms, while 5 signifies the number of oxygen atoms, while 18 signifies the total number of atoms, and 6 signifies the total number of oxygens. Now the size of the metal must match the size of the crown. As you can see, for an 18 crown 6, that's what you use for potassium. So the potassium metal is going to be sitting right in the middle there, and it can be trapped. Now, the advantage of using a crown ether is the fact that it's able to free the anion because it traps the cation. You see? And so normally metal ions are not soluble in low polarity solvents because they lack dipoles. However, in the presence of a crown ether, metal complexes should dissolve nicely because they can solvate the cation but free the anion. Now imagine how a crown ether could be used to aid reactions between ions, especially anions, in low polarity organic solvents. You can actually use the crown ether to seize the cation and release the anion in the process. Okay, look at this example. We know that the fluoride ion is heavily solvated by polar protic solvents. Okay, for instance, if you were to take, say, the fluoride in the presence of an alcohol, because of that interaction between the fluoride and the positive end of the hydrogens, of the ionizable protons, guess what? The fluoride is occluded, and so it cannot react. See, it cannot react. However, in the presence of a crown ether, the crown ether can solvate the potassium ion and free the fluoride nucleophile. So the fluoride nucleophile is now in solution. It's ready to react as a nucleophile because the potassium ion has been sequestered or solvated by the crown ether. See, Without the ground ether, the solubility of potassium fluoride in benzene is going to be impossible, because benzene is a non-polar solvent. So how are you going to get it to dissolve? It doesn't dissolve. That means that the fluoride cannot react as a nucleophile. But in the presence of a ground ether, this is now made possible. Generally, the fluoride ion is not used as a nucleophile because it is strongly solvated by strong polar solvents, like alcohols, like we saw. See, like alcohols will strongly solvate the fluoride and make it unreactive. Soft solvation greatly reduces its nucleophilic strength. However, in the presence of a ground ether, it is soluble enough in a non-polar solvent that it can attack the electrophile. So using a mixture of benzene, a non-polar solvent, right, the non-polar solvent, and the ground ether, you are able to trap the fluoride. See, the fluoride has been trapped. You see, the fluoride has been trapped like that, and you are now freeing the fluoride to act as a nucleophile. The fluoride can now act as a nucleophile. And because the fluoride is no longer stabilized, the energy of the fluoride is increased. See, the energy of the fluoride is increased. You're going to have the fluoride here versus here. You see, the energy of the fluoride is increased, and as a result, the reactive activation energy decreases and the reaction goes in the forward direction. Now, smaller ground ethers bind to smaller cations. Typically, a small ground ether like a 12 ground 4 will solvate a lithium, a 12 ground 5 will solvate a sodium ion, while a 12 and 18 ground 6 will solvate a potassium ion. So depending on the type of cation you want to solvate will determine what kind of ground ether that you use. Now, preparation of ethers. There are two ways of preparing ethers. You can either prepare symmetric ethers or asymmetric ethers. Now, diethyl ether is a symmetric ether. See, it is a symmetric ether. It is a symmetric ether, right? It is a symmetric ether. And it can be prepared by the acid catalyzed dehydration of ethanol. So if you have two alcohols, if you look at this, even though this is a bad leaving group, it can be protonated, and you have the formation of a good leaving group, and then the subsequent attack of the second molecule of ethanol in an SN2 fashion, and that leads to, upon the proton transfer, leads to the formation of a diethyl ether. Now, how is it a dehydration? It involves the loss of water, as we can see. It involves the loss of water. Now, this method is only good for symmetric ethers. This is only good for symmetric ethers. So this is good for symmetric ethers. Okay? For asymmetric ethers, it's not possible. Now, the preparation of ethers of asymmetric ethers, you have to use the Williamson synthesis. So for asymmetric ethers, you have to use the Williamson synthesis, which is a viable approach for making asymmetric ethers. And again, the reaction goes via an SN2. Okay, so the very first thing, you want to make your nucleophile. So you make your nucleophile, because using the base, and then you can now take the nucleophile and attack the carbon, and you have the loss of the leaving group, and you have the formation of your ether. You see, you have the formation of your asymmetric ether. Asymmetric ether. Okay, that's the formation of your asymmetric ether. Okay, and of course the halide that's left as a leaving group. The Williamson's ether synthesis is a viable approach for making asymmetric ethers. It's a very viable approach for making asymmetric ethers, as we saw. The alkoxide that forms in the first step is a strong base, okay, and because it's a strong base, you cannot bring it into the vicinity of a secondary or tertiary alkyl halide, because it's going to lead to an elimination. So this method is only good for methyl See, it's only good for methyl and primary alkyl bromides or bromides, right? You can use it for primary alkyl or you can use a primary alkyl halide in this case. Okay, all right. And so if you use the Williamson ether approach to prepare methyl tertiary butyl ether, MTBE, which is used as an additive in gasoline, you see, it is to do this kind of thing, you have to first make this into a nucleophile. So that's the first step, make it a nucleophile. Once you make this into a nucleophile, you can now make it react with a methyl iodide in an SN2 fashion, and you get MTBE. You cannot try to make the methanol into a nucleophile and then this is your electrophile. You see, it's not going to work. This is not going to work. No reaction. The reaction will not occur. That's because it goes SN2. In SN2, electrophile must be your electrophile must be methyl or primary alkyl halide, right? It has to be a methyl or primary alkyl halide. It is better to make your retrosynthetic disconnect on the methyl side. Why? Because, of course, if you're trying to go backwards, it's better to cut it off here. This is where the attachment occurs, because that's the only part that's going to go SN2. The other side will not. Okay. So typically, this is the best route. You make this into your nucleophile, and then this is your electrophile. Okay, this is your electrophile. Now, use the Williamson synthesis approach to synthesize the following molecule. As you can see here, we have to break it over here because this is where an SN2 will occur. So you need your electrophile. See, your electrophile is a primary alkyl. This is okay. Halide. And that's good for SN2. But your nucleophile, it doesn't matter. Even though it's bulky, it can still undergo SN2. See, nucleophile, even though it's bulky, can still undergo SN2. Now, preparation of ethers. Recall from 9.5 that oxymercuration demercuration can be used to synthesize ethers. We already learned that, right? And the reaction goes Markovnikov's, and it is believed that the addition is anti. Now, similar to oxymercuration, right? So basically, that's basically what it is. Oxymercuration demercuration. That's not new to any of us. Okay. The reaction of ethers, as we mentioned earlier, because they are aprotic, ethers are generally unreactive. However, ethers can react under the right conditions. Okay, they can react under the reactive side, of course, is the oxygen. Okay, and so you can make that react with the acid. Okay, it can act also. It is more likely to react with an acid. Okay, right, because it can be protonated. Okay, so ethers, because of that, can undergo acid promoted cleavage. And the reason why it's an acid promoted cleavage is because the acid is used up in the reaction. As you can see here, you have a proton transfer because this is acting as a Lewis, Bronsted-Lewis base, can pick up the proton, and then what happens is that the nucleophile attacks in an SN2 fashion, and you have the cleavage of the ether. Now, in the presence of an excess of the HX, you can have subsequent protonation of the alcohol again, and then the attack of the nucleophile again, and so you have complete replacement of the OH group with the halide. So this is just an example, as you can see here. Now, if you're going to draw the complete mechanism, it first begins with protonation. It begins with the proton transfer, and then the attack of the nucleophile. Okay. Now, we're going to begin with this in the next couple of slides because I want to point out something really important.